Hello and welcome everyone. So today I will be discussing about the linearity assumption drawback of PCA. So let's begin. So what are we going to cover in this lecture? First, I will briefly cover PCA and its key ideas. Will not go into too much detail because this is about the drawback and not about PCA itself. Next, I will talk about what is this linearity assumption? What does it even mean? And how is it even a drawback? Why are we calling it a drawback? The next we will see then how can we overcome this drawback? There is a very clever trick according to which we can overcome this drawback. I will come to it later. Next, we can talk a lot about theory, but until we do something in practical, we cannot say it really works. So I'll be presenting you with a code which will be comparing the standard PCA to our modified version of PCA, which overcomes this drawback. So, for a brief overview of PCA, all of us know that major uses of PCA are dimensionality reduction and feature extraction. We have studied about PCA. So, this is just like an refresher. How do we do all this? We project the data into a subspace of lower dimension, which encapsulates the maximum variability of data. So, we basically project the space, we transform the space such that we get orthogonal directions in which the s- the maximum variability of data is captured, and we select that subspace with lower dimension. Suppose we are 3D space, then we create new axis, and we suppose we have to transform the data into 2D space. We will select those two axes which captures the maximum variability of data, and thus we can get dimensionality reduction, and we can get the two most important features of data. So if we remember this example from class, these are genes which are features and these are examples which are mice. So this is the normal data plotted into 3D space. So what I am claiming is PC is nothing but a linear transformation. A very, what can I say? Very good looking linear transformation. Yeah. So what we did is we in class we centered the data, and then we calculated these axes PC1, PC2, and PC3. These are orthogonal axes called principal component 1, principal component 2, principal component 3. And the number beside it clearly shows that how much variability of data it captures. So, as I talked earlier, if we have to reduce it into a 2D space, so we say take PC1 and PC2, and we project the data into that space. Simple. So I had some data, I centered the data, and then I calculated the axis which captures the maximum variability of data. PC1 captures the maximum variability, PC2 is the next one, and PC3 is the last axis which captures the minimum variability. If I had to convert into a 2D plot, I took the first two axes and projected the data into that axis. If suppose I had to construct a 1D plot, then I would disregard every axis and I would just consider PC1, and I would project all the data onto that axis. So this is basically PCA. So like a lot of you might be saying, "Yeah, I know all this. I have learned PCA. What is new? कुछ नया बताओ." So let's talk about linearity assumption. Linearity assumption is evident. See, everything we did earlier was we reduced the mean from all the examples. So we centered the data, and then we did some sort of matrix multiplication to transform the space into the space with the principal components as our basis. Okay, and then projected the data. All this can be done by matrix multiplication. This is simple linear transformation. So all operations on data point leading to a transformation are linear. So we can represent it as a matrix multiplication. Here X is our input features, the input space, and the WN transpose is a matrix which will transform it into the feature space, and F is our features. So for kth input, this is the kth feature. So for how many inputs we have, we can calculate that many features. and then we can choose the most important features. See, this is Wn is a projection matrix, F are the features, and X are the normalized data, raw data at the kth instant. So for what do we do in PCA? How is this linear transformation PCA? So if we calculate the covariance matrix of the input features, this C matrix, and we diagonalize it, then this V matrix will contain the eigenvectors, and this will contain this is a diagonal matrix. So this matrix will correspond to our projection matrix. This is the weight matrix. If we multiply this transpose with our input features, we'll get the output features. So this is simply PCA. Okay. So we can see these are just matrix multiplications, and we know are linear. So what is the problem with linearity? Why did we say it is a drawback? Okay, so just because something is linear, I cannot call it a drawback. I have to substantiate it with enough reasons. So I don't see a problem here. See, there is a data in 3D space. I applied PCA and I converted into 2D space, PC1, PC2, which contains the data. PC1 has a maximum variability, PC2 has the second most variability. The same stuff. So there is no problem. We can see separate features. We can extract the two most important features, and all that can be done. So what is the problem? We again go to that point. So this is a very convenient example of data in which everything happens in a very good looking way. But in real life, data samples are not always this clean. It is not linear. We have non-linear relationships between features. Here we can clearly see for this data, for lower value of, or the value around 0 of x1, we'll have this kind of value of x2. So all the features are similarly linearly related. We can if we pay enough attention, we can think about simple linear relations between x naught, x1, and x2. But what if we have data like this? This is some isotropic toy model of data generated, where this is feature 0 and this is feature 1. If I have to transform this data, I have to extract features from this data, then how will I do this? Because in any direction I see, the variability is somewhat similar. And this data, the input features are not linearly related. So we cannot directly apply PCA in this case. So this is the drawback of PCA. In such kind of data, PCA fails. But so what should we do? If it fails, should we just sit back and say, oh, it failed, I will not see this data? We cannot do that, right? We have to think of some clever ideas, some clever ways, so that we can extract features from this data also. And thankfully, we are not dumb and we thought of some clever ideas. So what is the clever idea? Project data into some higher dimension and then apply PCA. Simple. Okay, that's not that simple. So I will go on and explain what does that mean. Say we have this data, and the first one, the data in original space. We can clearly see it's difficult to separate data by a line. It's not linearly related. It's somewhat random. So we did something and we projected into this feature space, the second column, and we can clearly see now we can see a plane which passes through the middle of the blue and the red regions and separates the data. If we project this data into a 2D plane, say on the side, on one of the sides or in the front, we can clearly see a line will be able to separate the data. So this is the data which is not linearly related, and this is difficult to separate, difficult to extract features. We projected it into a feature space by some sort of clever techniques, and then we can clearly extract features. We can clearly reduce the dimension of data and see in which direction the data has the maximum variability. So this is the same thing. If you see this from the top view, the third column, you can see it resembles the first one. But if we project it into some other direction, not the top view, we can probably separate the data better. So we did what? We just projected the data into higher dimension, and then we can apply PCA very easily. Okay. So similarly, the second example is there. You can see the in the second column, it is similarly easier to separate data and apply PCA. While in the first column and the third columns, it seems like impossible to get some valid result with PC. So how is it done? Like, let's just quickly go through some mathematics. I will not go into details because what was the aim of this lecture was to get this intuition of how what is the drawback and how are we overcoming it. So phi of x is some nonlinear transformation. We can apply some nonlinear transformation to the input features and then apply your PCA, which is basically linear transformation, and get the features. But there is some problem in this basic technique that phi of x is unknown. How will we apply that linear transformation? And it is also difficult to design. So we come up with a clever trick known as the kernel trick. So instead of applying nonlinear transformation to the features, we replace this covariance matrix with a kernel matrix whose elements are denoted by this, where we for the ith and ijth element of the kernel matrix, we put the ith feature of input feature and the jth input feature into this kernel function, and we get that element of the kernel matrix. So upon applying this trick, our kernel, our nonlinear transformation will be equivalent to this. This features, the kth feature will look like this. So let us compare this with the normal PCA. See, our features, kth feature look like this. A simple linear transformation, multiplication of matrix with the kth input feature. But with the kernel trick, it looks something like this. It may look complicated at the beginning, but it's not that complicated if you look closely. It's just a nonlinear transformation with this kernel matrix. And we get this feature, output feature. So these are some common kernel functions. One can look into it later. There's some Gaussian radial basis function, polykernel function, sigmoid kernel function. There are many such functions. These are some examples I have placed to get an idea. So is it the time to code? So I will demonstrate what I just said in a better way, and what better way than to code it and visualize the matrices. So this is a blocks of code I have written. Oh, so I will run these cells and then we'll discuss this. So I have done the first two cells, and see, we are basically creating a toy data for understanding this from the first two cells. So this is the training data. This is the same data we saw earlier in the slides. So it is difficult to separate from PCA. So we'll see how it is difficult. And this is the test data, which is somewhat similar to the training data. This is the zeroth feature. This is the first feature. Okay. Now I will move on to demonstrate how is PCA different after applying this trick and how is this data not separable by PCA. So after running these blocks of code, so see, this was our test data. Okay. So this is the zeroth feature in the x direction and the first feature in the y direction. Even after applying PCA, the data doesn't change much. It's very similar. You can say maybe it has rotated a bit in some direction or transformed a little bit. But in the x and y axis, it is written principal component 0 and principal component 1. But it has not really done anything new to the data. PCA was just waste of compute. We didn't do anything with the data. The data looks the same. But what we apply this kernel function. When we apply this kernel function, then projection of test data using kernel PCA, see the data has separated. In the zeroth principal component in the higher dimension in which we transform the data, and this is the first principal component in the y-axis, and the data looks like something like this. So now it is very easy, it's clear to how do we will extract features, suppose, and get the data, because now the data is not isotropic anymore. Okay, so I think I was able to make my point clear. So if anybody is interested to know, here we are using the radial basis function as our kernel. So this was about the drawback of PCA with the which is called linearity assumption, and how we can overcome this. Hope I was able to explain it appropriately. Thank you.